Have you ever stood at the edge of a precipice, peering into an abyss of undiscovered potential? Imagine this. Large language models, or LLMs as we fondly call them, are like these adventurous explorers, probing the deep, dark depths of in-context learning. Yes, these digital trailblazers have a knack for picking up new tasks from a smattering of input-output instances, aptly coined as shots. These shots are deftly planted before a test input and unveiled within the LLM's perceptive context. But here's the catch: this method, all roses. The context window of an LLM, akin to the capacity of a sturdy backpack, restricts the amount of shots they can pack in for each adventurous expedition of in-context learning. This boundary has turned previous research into a cautious hiker, sticking to the well-trodden path of few-shot learning. Sure, the path is comforting, but few-shot learning can sometimes be as vague as a foggy mountain pass when it comes to defining tasks due to its limited context. Nonetheless, the journey of few-shot learning has its charm. So you might be pondering, what does many-shot in-context learning entail? This refers to the method where large language models, also known as LLMs, acquire knowledge from a vast number of input-output samples, dubbed as shots. These samples presented within the context of the LLM itself. Perhaps you've heard of few-shot learning, a method that can seem ambiguous due to the scarcity of examples. In contrast, many-shot learning offers a more definitive task specification. It's like comparing a vague sketch to a detailed picture. The more shots you have, the clearer the model's task becomes. The main difference lies in the quantity and detail of examples, with many-shot learning providing a more comprehensive set of data. The question you might be asking now is this achievable? The answer lies in the leaps and bounds made technology, where the context windows of publicly available LLMs have broadened by at least 100 times. This means that LLMs like Gemini 1.5 Pro can handle up to 1 million tokens, as opposed to a few thousand tokens with models like GPT-3 and Llama. Let's journey through the myriad benefits that many-shot in-context learning offers over few-shot learning. As we amplify the number of input-output examples, also known as shots, we witness a notable advancement in performance spanning a vast range of tasks. Take, for example, mathematical problem-solving tasks, where many-shot learning leaves its few-shot equivalent far behind. This also rings true for question-answering tasks, where the capacity to process a greater number of examples results in much more precise and exhaustive answers. In the case of summarization tasks, many-shot learning is advantageous due to its ability to generate contextually rich summaries. Other domains recording a significant uplift include algorithmic reasoning, outcome-reward modeling, low-resource machine translation, planning, and even sentiment analysis. By broadening the context window and integrating more examples, we are able to augment the precision and adaptability of large language models. What lies ahead for many-shot in-context learning? As we advance further into the realm of this fascinating field, we're looking towards innovative solutions to circumvent the restrictions of human-generated outputs. Two potential avenues, specifically reinforced in-context learning and unsupervised in-context learning, present riveting prospects. Reinforced in-context learning employs model-generated rationales in place of human ones. This strategy could potentially streamline the learning journey and result in more effective outcomes. Conversely, unsupervised in-context learning with rationales completely, urging the model only with domain-specific inputs. This method be particularly potent for intricate reasoning tasks in the many-shot regime. However, one of the most enticing aspects of many-shot learning is its capability to overrule pre-training biases and learn high-dimensional functions with numerical inputs. This indicates that the model isn't merely echoing information, it's genuinely learning and adapting. Let's delve deeper into the complications of many-shot in-context learning. Many-shot learning's potential is genuinely recognized when the shots tally escalates into the hundreds of thousands. Despite seeming like a daunting endeavor, the results make the exertion worthwhile. Nevertheless, this approach has its limitations, often demanding superior quality, human-made outcomes. This is precisely where reinforced in-context learning and unsupervised in-context learning come into play, circumventing these obstacles. Reinforced ICL replaces human-composed explanations with those created by the model, using the accuracy of solutions as a filter for in-context learning. This method could likely simplify the overall learning process, leading to more effective results. In contrast, unsupervised ICL presents the model with problems alone, rather than problem-answer pairs, proving particularly efficient for complex reasoning tasks within the many-shot regime. Interestingly, the order of examples can significantly influence ICL performance, even within the many-shot context. This highlights that the model isn't merely reciting information, but is truly learning and adapting. It's crucial to note that the popular next token prediction loss method might not invariably forecast ICL performance for problem-solving and reasoning tasks. Our key contributions comprise the scaling of in-context learning, ICL, the application of reinforced and unsupervised ICL, and the analysis of ICL performance. Let's delve into the potential of scaling in-context learning, a pivotal facet of many-shot in-context learning. In-context learning, also known as ICL, is a game-changing method that equips large language models, LLMs, with the ability to learn new tasks on the fly. But how does it accomplish this? It commences with examples provided only at inference time, allowing the model to learn and modify its responses in real time to the information offered. But what makes it tick? During the in-context learning training, the large language model is presented with a prompt containing a series of input-output examples, or shots. These shots are crucial to the learning process, illuminating task and guiding the LLM. But shots are not the only tools at LLM's disposal. A test input is introduced at the end of the prompt, creating another hurdle for the LLM. The model then predicts the upcoming tokens based on the prompt in an auto-regressive manner, using previous tokens as a foundation for the next one. Significantly, in-context learning is a stark departure from task-specific fine-tuning. While the latter involves optimizing model parameters, the former does not. It enables large language a diverse range of tasks at inference without the need for preset parameters. The increasing size of context windows in large language models in recent years has allowed the use of many more shots for in-context learning than typically applied. This subtle shift sets the stage for the of many-shot in-context learning. What distinguishes this from few-shot ICL? The key difference lies in resource utilization. Many-shot learning can take advantage of larger available fine-tuning datasets compared to its counterpart. This novel could potentially reconstruct our understanding of task-specific fine-tuning. It could even render it superfluous in some instances, diminishing the need for specialization and enabling large language models to address a wider variety of tasks without task-specific fine-tuning. But the advantages of many-shot in-context learning extend beyond that. Exposure to a diverse array of ICL examples could lead to enhanced generalization, equipping the LLM to tackle more intricate problems than few-shot in-context learning can handle. Plus, it provides superior control over model outputs, mitigating biases that may arise from pre-training. To sum up, scaling in-context learning is a potential game changer. Game changer. It's not just about enhancing the efficiency or accuracy of large language models. It's about broadening the scope of possibilities and reshaping the future of many-shot in-context learning. Exploring the practical applications of many-shot in-context learning, we see its utility across several different areas. Let's delve into a few instances. Our first stop is the logistics sector. Here, the objective is to transport parcels within and between cities. Evaluating the common-sense planning capabilities of large language models in this area, we found that in-context learning substantially boosts success rates as the number of shots increase. The results aren't quite at par with cutting-edge planning methodologies yet. They do spotlight the potential of many-shot to boost the common-sense planning abilities of LLMs. Moving on, we journey into the realm of code verification. Enhancing LLM reasoning often involves test time verification, where the LLM proposes multiple candidate solutions for a particular problem. A trained verifier then ranks these solutions and chooses the best one. Our goal was to train such verifiers in context, with correct and incorrect code-based solutions. The outcomes were encouraging. As the number of in-context examples increased, we noticed a noteworthy improvement in accuracy, indicating that the LLM gets better at verifying the correctness of solutions through many-shot ICL. But what if tasks lack high-quality human-made rationales or demonstrations? Many-shot ICL excels here as well. We introduced reinforced ICL, using model-generated rationales for in-context learning. Despite the risk of false positives, in most instances, we found model-generated rationales to be as efficient, or even more so, than human-written rationales. To sum up, many-shot in context learning not only shows theoretical promise, but also manifests practical success in numerous areas, from logistics planning to code verification. In the realm of problem solving, allow me to illustrate the effectiveness of many-shot in context learning through a fascinating case study. Our study focused on the application of reinforced and unsupervised in-context learning to the Hendrix math dataset. This dataset consists of intense competition-level math problems that high school students grapple with. The results were quite unexpected. Both and unsupervised in-context learning, the traditional in-context learning model that uses ground truth solutions in both few-shot and many-shot learning scenarios. In a surprising twist, many-shot in-context learning performed at par, or even better using only problems, as opposed to using problems coupled with solutions. This implies that solutions may not always be necessary for in-context learning within this domain. For a more comprehensive understanding, we extended our study to the GSM-8K dataset, which has a distinctly different distribution of problems than the Hendrix math dataset. Our was rewarded as the reinforced in-context learning model, when fed with math prompts, outclassed the traditional in-context learning model with ground truth math solutions and unsupervised in-context learning in many-shot settings. Our exploration didn't stop there. We applied many-shot in-context learning the Google Proof QA GPQA benchmark, a multiple-choice QA base that emphasizes on graduate-level reasoning in physics and chemistry. The accuracy of the test significantly improved from 5 shots to 125 shots. Interestingly, model generated on GPQA appeared to be superior to ground truth rationales up to 25 shots. Finally, we put reinforced in-context learning to the test on Big Bench Hard, A of challenging algorithmic reasoning tasks. The results were in-context learning outperformed the standard 3-shot COTI prompt for nearly all tasks, indicating that model-generated rationales can sometimes outdo human-written, even with the same amount of data. Let's venture into the realm of many-shot in-context learning, often referred to as ICL, and scrutinize its potential to counteract pre-training biases in large language models, LLMs. To begin, we must acknowledge an ongoing issue in the field: pre-training biases. It's no secret that while LLMs have the capacity to learn new tasks, they exhibit difficulty in relinquishing biases from their pre-training phase. A study by Koss et al. In 2023 brought this issue to light, its main focus being few-shot ICL challenged by LLM context length limitations. We thought it necessary to re-examine their research, putting many-shot ICL under the microscope. For this investigation, we employed the financial sentiment analysis dataset. This dataset was a perfect fit our study as it facilitated exploration of label relationships that counteracted pre-training preferences. We implemented 2 label transformations: flipped labels, involved rotating default labels, and abstract labels, where unrelated labels were incorporated. The findings were nothing short of fascinating. With few shots, the accuracy with replacement labels fell drastically compared to default labels, revealing a struggle to overcome ingrained biases. However, as we increased the number of shots, performance saw a marked improvement, leading us to believe that LLMs can indeed shake off pre-training biases when provided with enough in-context examples. Next, we wanted to test the waters of non-natural language tasks and evaluate many-shot ICL's proficiency in learning abstract mathematical functions with numerical inputs. We focused on parity functions and high-dimensional linear classification. The results were encouraging, as many-shot ICL managed to beat random chance accuracy and match the efficacy of a robust baseline, like k-nearest neighbors. Our final aim was to determine if many-shot ICL is influenced by example, a trait seen in few-shot ICL. The outcomes were unexpected, revealing performance fluctuations across different sub-areas in Math 500. This indicates that ensuring dependable results with many-shot ICL in long-context models is a challenge yet be overcome. In this part of our discussion, we delve deep into the fascinating paradox associated with negative log likelihood, or NLL, in the realm of in-context learning. Conventionally, it's thought that as the context length expands, the NLL for ground truth test results linked to the next token prediction loss decreases predictably. This concept would naturally lead us to assume that NLL patterns could serve as a valuable indicator of downstream performance. However, our research indicates that the reality might be quite different. Surprisingly, we discovered that NLL patterns do not strongly correlate with downstream task. This suggests that a diminishing NLL doesn't assure an enhancement in the performance of the task in question. This unexpected underscores the intricate and complex characteristics of many-shot in-context learning. Worth mentioning, however, that our research was carried out using a model, and while this allowed us a controlled environment to conduct our analysis, our conclusions might hold for all models. Moreover, the question of why performance might sometimes falter with a greater number of examples in the prompt remains unanswered. It's an intriguing query that deserves more thorough exploration. Well, that was a deep dive into the world of many-shot in-context learning. We hope you found our exploration into this complex and fascinating topic as intriguing as we did. We've covered everything from the limitations and advantages of many-shot in-context learning to the practical applications, case studies, and even the paradox of negative log likelihood. We're grateful you've joined us on this journey, and we hope it's provided you with valuable insights and a deeper understanding of this innovative approach to machine learning. If you've found this video informative and engaging, please show your support by liking this video. And if you're as captivated by the potential of many-shot in-context learning as we are, be sure to subscribe to our channel for more deep dives into the fascinating world of machine learning and artificial intelligence. Don't forget to hit the bell icon to ensure you never miss an update from us. Remember, every like, subscribe, and bell notification brings you one step closer to becoming a many-shot in-context learning expert. So, what are you waiting for? Dive in.